Oh,
Welcome to day 3. We're gonna dive back into it. We don't have, I usually like to start classes with announcements right away. We don't have too much going on at the moment. I will be working on getting a first assignment up. You can expect that sometime over the next few days. I don't yet know whether that will be due next Wednesday or the Wednesday after that. I have to decide based on where we are in what we're covering. And again, this is the first time I've taught this course. Don't have a sense of what flow is going to be optimal yet. And I will, of course, work with you to figure out what that flow will be as I design assignments. Want to make sure that they are turned in, that you get feedback on those ahead of an exam that covers that material. So there will probably be some schedule shuffling as that comes to pass.
oh, hey, one more thing I should probably tell you.
Yeah.
I think, you and Karen know each other. Are you two good friends?
I wouldn't say we're good friends, but we know each other.
Well, I think you should try to talk to her about that because she has a lot of experience in teaching a class for the first time that she has never taught before.
Me too.
So,
I just have done it so many times that I know not to expect perfection.
well,
And to expect that I know what I'm doing completely without student feedback. I think as someone who's in the class of a first time class, communication is the only way to get it right. To make sure that everyone is on the same page, that expectations are clear, and that I am working with you to make sure that you are performing the best that you are able, given the constraints of I haven't done this 5 times before or 6 times before.
well, thank you for your honesty anyway. And before we get started, happy April Fool's Day.
Woohoo! If it was the first day of class, I'd have some things planned, but I'm not really an April Fool's person usually. But yes, happy April Fool's to everyone. Hopefully you aren't pranked too hard.
Honestly speaking, I rarely ever do get pranked on April Fool's Day. Regardless, I just hope, I just wanted to make sure everyone's got the appreciation in this class. Now, shall we begin?
Begin. Last time we were talking about comparing a couple of different algorithms. How would you compare 2 different competing algorithms to solve the same problem? So we looked at a couple of main rules that we can use to simplify an expression in terms of just its asymptotic notation. The first was that we can remove lower order terms. There was a dominating term that as n grew to be large enough to make a difference, one term dominated another term, and we can, for all intents and purposes, ignore the lower order term. The other was that constant factors remain constant regardless of the size of that input. So an algorithm that runs 100 times faster at input size 10 would run 100 times faster at input size 1 million. And so we also ignore that with respect to the running times of the algorithm because we care about how things change as the input size grows. So we had one example of this, and we're going to get through another example. Here is algorithm 1, and here is algorithm 2. So what are the associated running times of algorithms 1 and 2? Take a second, think about it. We'll come together and get an answer.
Oh.
Yeah. 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 Algorithm 1 is cubic. This makes sense. This follows the same rules that we talked about last time. There are 3 lower order terms, bn squared, cn, and d. A is a constant. We can ignore it. So this is just a cubic function. The second, though, we have to distribute.
Yeah,
We get n squared plus n over
divided by
2.
two, yeah. And I think that is a quadratic.
Mhm. Yeah, if we end up with n squared plus n over 2, then we have the over 2 is a constant, that goes away. The n is a lower order term, that goes away. We end up with something that is quadratic. Need to do something about this, I keep forgetting. I hate it. I'm smearing my board. Much better. Not really. Further examples. 2 more.
N factorial,
N factorial.
that's,
I have to put jokes wherever I can in my slides. I really want to be excited about it.
You're close.
Right, right. Much better than if it were X or some other inferior variable.
Oh.
So n factorial is not something that was on the prior list, but
it's very familiar, please continue.
but we can compare it in a mathematical way to an existing order that we have seen before, or we could see before. So what are some functions that are mathematically similar to, but not equivalent to, a factorial?
With the Fibonacci sequence we said on.
Intriguing,
Well, you're not.
but not quite. Not one that I'm looking for. It's a good guess. Yeah,
Like n times n minus 1 times.
yeah, as a factorial. So
Yeah,
n factorial is n times n minus 1 times n minus 2 all the way down to 1. How would we represent something like 2 to the n?
that is exponential.
It is exponential. If we were to draw it out in a similar way and do that, yeah. 2 times 2 times 2 times 2.
Yeah,
The appropriate number of terms, there are n terms of times 2. Actually end up with a times 2 down here. How does this compare to that? Which one's larger?
well, yeah,
Factorial is larger because n is greater than 2, n minus 1 is greater than 2, n minus 2 is greater than 2,
It's like really
2
hard
is
to get
equal to
around
2.
it. Don't like worry about it too much. And we'll be back in like 15 minutes or so. So if you want to be here.
How would we handle something like n to the n?
N times n.
Yeah.
yeah,
N times n times n times n times n. And now n is equal to n is greater than n minus 1, n is greater than n minus 2, etc. So we can place factorial somewhere in between 2 to the n and n to the n.
you got it.
So it is, you can always find something that is lower than, something that is greater than, and it places bounds on factorial. I think the first time that I learned about factorial as a function, it just felt like, all right, it's bigger than 2 to the n. Okay. But placing it within those bounds shows that it is between an exponential with base 2 and an exponential with base n. Makes sense. So knowing this, can we map this concept of a factorial to an algorithm that has that running time? Has anyone seen or heard or can think of an algorithm that runs in factorial time? Yeah,
I think recursive Fibonacci.
recursive Fibonacci.
Well, not entirely wrong anyway.
Close. That actually might work. Recursive Fibonacci without overlapping subproblems, I assume. Yeah. We'll talk about dynamic programming later in the term, but if we're handling this in an unintelligent way, then quite possibly. The example that I want to share is BOGO sort.
Logos.
Have people heard of BOGO sort? Yeah,
That's sort of where there is.
it is certainly a fun one. So for those who don't know what BOGO sort is,
I admit, I'm actually ashamed I've never heard of it before.
because no one should ever use it.
Really?
It's a classroom entity only. All right, BOGO sort, or as I prefer to rename it, bozo sort, is we are going to randomly permute the array or the list, check if it's in order. If it is, we're done. If not, randomly permute it. And continue this process until it is sorted. This is why they should never be done in practice. This is silly, but it maps directly onto a factorial. Can anyone see why? Why does this concept of randomly permuting a list until it is in order map to a running time that is factorial? Yeah.
It's kind of like a depth cards where it can be put in any way.
Yes. How many permutations will we need in order to, for the first time, on average, get the lowest value in the correct place? So let's say we're sorting a list of 5 numbers. How many permutations will you need on average, random permutations, before you get a 1 in the first place?
Probably in.
The 5? Yeah. Yeah. So that's where the n term comes from, is it's going to take you n permutations on average. This is just a geometric progression. Given that the first one is in place, it will only be in place every 5 times on average, since there are 1, 2, 3, 4, 5 possibilities for what could go in that first position. So only 1 in 5 times will we get the first thing in the right position. Given that the first one is in the right position, how many times do we need to permute in order to get the second one in the correct position? 4 times, given that the first one is in, so we have 5 times 4. Given that the first 2 are in position, how many times do we need to permute to get the third one in place?
3.
3 times. So we start to see how this becomes the factorial sequence as the size of the list grows, the size of n for the factorial grows. So we'll discuss, I actually don't know if we'll discuss ways to sort. This is again pulled from data structures, and I think sorting was covered very well in data structures.
Very well. Thank you
So,
very much for asking. We went through a lot of sorting. That
yes.
includes with linked lists, CW linked lists. I don't need to go into all that.
Oh yeah.
But I fondly remember it.
So we can, of course, run our program to decide its running time, but let's tie this now back to the actual lines of code and look at analyzing this in terms of, we have a program in front of us, how can we determine its running time from that? We can recall that programs are just made up of operations. If we could count the number of operations, we could then plot on the x-axis the size of the input, and on the y-axis the number of operations that are needed to complete the algorithm. And whatever function best fit that would be the function that defines its running time as the input scales. Of course, running it for every possible value and then coming up with, how are you going to come up with the function of best fit? If it looks kind of like a line, you could use linear regression. If it looks kind of like a curve, you'd have to use quadratic regression, cubic regression, quartic regression, quintic regression. This sounds problematic to try to find the exact function that is fitting it. So it works better if we can look at the exact lines of code within that itself. Let's look at the linked list size method as an example. Who recalls how a linked list determines its size.
I remember.
Yeah,
Yeah, so, yeah, a linked list tends to just determine its size depending on how many elements there are until it reaches the end of the list.
so on a line by line basis, what's it doing?
Well, I think of the words here, honestly.
Good.
But every time you added a node, you just had like a size variable that you.
Yeah,
Bingo, that's the one.
there you go. If you carry a field in your object that keeps track of the size, when you call, add, or remove, then it just queries the size. And that way you
Pretty
don't
much.
have to go iteratively find the size every time we care about the size. What does that save us in terms of complexity? It turns something that is linear into something that's constant. It doesn't matter how big the list is, if we have kept up with its size as we built it, it knows how big it is. So it doesn't need to recalculate that, it just needs to look it up, which ends up being a very similar type of time-saving move that we will make in this class many a time as we're looking to reduce the complexity of the algorithms that we write. So single operation, it is constant complexity. So that tells us, we'll define theta of one momentarily, but theta of one says that it takes a constant amount of time to tell us the size of the list, regardless of the size of the list. It takes the same time to tell us that if the list is size 1 as if the list is size 10,000. If we didn't have a size field, and we had to iterate over the list every time we queried the size, then we would need to start at the head, check the heads next, check that node's next, check that node's next, check that node's next, until we find the tail, or until the next is null. If we do that, then it's going to take us time proportional to the size of the list. And now a list of size 10,000 will take much longer than a list of size 1 to calculate its size. So two different algorithms of ways of calculating the same thing, but when we go to actually compare them, one is better than the other. Both of them would be complete and correct algorithms, but one is significantly less efficient than the other.
Okay. Yeah.
Here is such a size method. Let's actually go through this and start to draw out a table for size 1, size 2, size 3, and size n. So we're going to go through, think of this from exactly the code that is displayed, and I can blow this up a little bit since this is probably hard to see for people at the far points of the room. If I blow it up, I'm going to lose the table.
Smart. Let's see, for a list of size, 1, 2,
try to-
3, and okay, so
Build this table and write it out, and let's let everybody work on this for a bit. You can work with a partner if you'd like to, or a group of 3 or 4 people who are around you. Let's work on this together and see if we can build out this table.
all right, let's see. It's telling so starts with that. That's definitely one. The thing. I recognize a lot of this. This is a for loop continuing. And ton of complexity or operations. So for this list, it says, operations. Let's think of that. Kind of operations. 1, 2, 3, 4. How many operations do you think are next? Well, think I have an idea. Let's start by setting up a.
Yeah.
What does the get next function entail? Is it just?
Yeah, I
dropping
actually
down
have
the
something
list,
here that-
Or is it going through each time?
I'm going to assume that this is just one function or one operation.
Okay, cool.
Okay. In operation.
Yeah, operations, lines of code that are being executed. If we're looking at for other methods that are, you'll use a best guess usually to say, if you were implementing get next, how would you do that? And you would probably need at least 3 in practice, but we're going to assume this is possible in just one.
One, two.
Wouldn't it also depend if
Yes, you can make either assumption you care for. I personally hate them.
dummy head?
Yes.
I actually agree with you on that. Is super, super annoying. Yeah, that too. Oh, let's see.
Yeah,
I think I have pretty good guess.
pretty good guess so far.
Yeah, is it a 3 plus 3? Just the way I'm looking at it. Operations that only occur once like tally to 0, the
Yep.
utilization of the node being the thing like occur. I say, oh, and it's such a full year for each. Like, it has to like check this null. And do so next, I will actually.
Yep, that looks great. Yeah, let's go through this a bit. So when size is 1. I apologize to people who are half a mile away from me, all the way in the back. But we have, when size is 1, we have to set tally to 0. So I'll just keep note of what's happening. The 4 is going to do this a single time. We need to check whether node is null. Node is currently front. We're going to go in and do the tally plus plus, which turns tally to 1. Then we're going to do node equals node dot get next. Loop back around. This should now be null. Since we're looking at the nodes dot get next, if the very first node was the only, the node should be null. So this check, which happens again, now sees that it is null. And we return. Each of those are a function of some kind, or something of some kind. So we have 1, 2, 3, 4, 5, 6, 7 operations. Let's run through it for size 2. Well, everything that we've already done has already happened, except that the node on the second pass is no longer null. So we need to come in and run the inside of the loop again. We need to prepare for the next pass through the loop. And we need to check for null. Now it will be null, so we'll fall through and return just that once. How many tally marks did we add? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we'll find that there are some of these that we do once, no matter what. And there are some of them that we will repeat and do every single time. We need to look at another node. So everywhere that there is a 1 happens once. That happens once. This happens once. Everywhere we see a 2 is happening n times. So we're going to check this value n times. We're going to check this value n times, and we're going to check this value n plus 1 times. The reason we check this n plus 1 times is we also have to check it the time we don't go do anything in the loop. So we're not going to check for the next pass through the loop we're not going to go into the loop at all, but we have to check, see the failure. So this happens n+1 times instead of n times. If we sum all of these together, we will end up with an expression. So what we see here is we see 3 copies of n and 1, 2, 3, 4 constant. So we end up with an expression that maps to a running time. How are we going to analyze this in terms of its asymptotic notation or asymptotic complexity? What can we ignore from our 3n+4? Constant can go away. The lower order term can go away. So this is in theta of n, because that is the largest order term with its constant stripped from the front. Regardless of the size, this now tells us approximately how much work this is going to be. Any questions on how that was derived or thinking about analyzing code in terms of how many times each line is run and building an expression from that process? Okay.
The smears are annoying.
They are, aren't they? At least the backside, it's a little bit better. I'll get this fixed. There's no way to avoid them. Guess I can use a red.
And spread the error. No, also not the error, the white bit.
All right, so we've analyzed and come up with a mathematical function. That should be exactly what I did. And we found an asymptotic order. No further questions?
I do not think so.
All right. Let's do the same thing again.
Public deck cards. Oh. Come up with a function describing its runtime. What order is your function in? Okay.
We're going to assume that these constants, spades, clubs, etc., are mapped to integers.
What do you mean by mapped integers? I've not heard that phrase. What is that?
So yeah, we end up with class constants. If you were defining the card class, you could do something outside of that that is
I think I know what you're talking. Okay. Now I understand. Thank you.
yeah. So all this is doing is iterating through the suits. So it should only run as many times as there are suits in a card deck.
That is definitely a nested for loop.
So feel free to work with people around you again as you like. As we will come up with some kind of asymptotic notation for what's going on here.
Yeah. Really see where you're going with that. Yeah, right. Right. Explains nothing first. Okay, let's start this. Yeah, so. We all take two parts. Something might be missing. Or nested. But I think I got it. This.
What are we doing? What have we found? Yeah,
My assumption is that it have to be like n to one thing. Because even with the other like lines of code like hard.
Mhm.
Two sides equal zero. It's like, well, even with all that, we're gonna get rid of the constant at the end anyway.
that's true.
So I'd assume it'd be.
And to the something, we have something polynomial. It's a good start.
You're not, I don't think you're wrong. I feel like, truth be told, I think it might be missing something regarding, well. The fact
Thing
that,
to note is we actually have two different variables here. Whenever we use n typically just means the size of the input, but we have two variables here. We have both a suit and a rank. So we want to incorporate those variables into the expression because they aren't the same size.
they are not.
So we would want an expression that contains both rank and size where possible. Yeah,
Yeah, I think that's what we were saying is that like, the suit is like n over 4, right? Because there's 4 suits, and then the rank is like n over 13.
Yeah, there are 13 of those, yeah. Yeah, so if we just say something like this is n squared, is it 4 squared, is it 13 squared? Those are very different numbers. How do we mess with that? How do we figure this out? So very similarly to what we did before, let me just go over this and we can see how many times something is run. So we make a new card array once. We're going to we allocate that memory. Regardless of the amount of memory it is, that allocation is a single procedure. Setting size to 0 happens once. This for loop is going to be run once to set up the suit, but comparing the suit to the last suit to see if we are done yet is going to happen suit plus 1 times. Can anyone explain why it's suit plus 1?
Well, it's the same type of logic with the last for loop, because we're immediately starting like at the beginning and we've already put suit at card dot spades. I'm trying to think of the right words here.
Yes. So just like before, anyone else want to give it a shot?
Check the clubs at the end.
Yeah, we have to
Yes,
check
we do.
the termination condition at the end. So we're gonna check it for each time we go into the loop and then check it one time when we fail to go into the loop. When we know that the loop is over. So it's going to happen the number of suits times. We'll go into it when suit is card dot spades, when it's card dot hearts, card dot diamonds, and card dot clubs. And then we need to check again once this is bumped up, suit plus plus is eventually going to become 5, for which there is 5 is not less than or equal to 4, as defined by our class constants. So we would terminate that outermost loop. So this runs s plus 1 times. Inside of this loop, we now need to figure out, given that this loop is running s times, everything that would happen once on a per loop basis is now happening s times, because the loop is being run s times. So how many times are we setting the rank to card dot ace? We need to do it when the suit is card dot spades. We need to do it when the suit is card dot diamonds, card dot hearts, and card dot clubs. I flipped hearts and diamonds in there since I know it doesn't define which one it is. I should probably be consistent. And comparing the rank to card dot king is going to happen r plus 1 times s times. How do we get that?
Well, it's for the same reason as plus 1, except you have that.
S times. Yeah. So for each rank, we're going to be comparing card dot ace is going to be 0, 1. We'll assume it's 1. Card dot king is going to be 12, 13. So this would run 13 times, but it's also going to run 1 more time to determine failure. That's your r plus 1. And since this entire thing is happening s times from the outermost loop, we multiply. Does it make sense why we multiply there? We have a for each time one thing happens, something else happens. For each day you wake up, you eat 3 meals. How many meals do we eat? The number of times we wake up times the number of meals we eat per day. So when we have a loop inside of a loop, we're running the innermost loop. Each time we run the outermost loop. The entirety of the innermost loop. There's a breakfast, lunch, and dinner on every day. So that's how we get that r plus 1 times s. How many times do we bump up the rank? Every time we go into the loop, that's r times s. We don't do that the time that we check the termination condition and it doesn't work. Same thing for everything inside of that loop. So if we're going to sum all of this up like we did before, what do we have? We can count all of the one-step onces. We have 1, 2, 3, 4 of those. So at the end of this, there's going to be a plus 4. We need to figure out, we have an S, and an S plus one. That is 3S plus one. Then we have an R times S, R times S, R times S, and an R plus one times S. How do we handle that? Distribute S into this. This becomes SR, or I guess I'm going to use RS again, plus S. Now we have 4 copies of R times S and 1 extra copy of S. The extra copy of S can go here. And we have 4 copies of R times S. Look right. How do we figure out what terms are lower order so that we can get an asymptotic notation for this?
It's just linear, right?
It would be linear in terms of as long as we're considering this R and S to be a single variable or this R times S to be a single variable. I would call this quadratic because R is a variable that can scale, S is a variable that can scale. If we were to define our own set of cards that had more than 4 ranks, but had 763 ranks and 14,200 suits, as we scale the ranks and the suits, then that would scale in 2 dimensions. So even though they are fixed, rank is a particular value, suit is a particular value. When this happens, you could call this constant. Since we're not really scaling the size of the deck, but our variables here are rank and suit, which we could scale. So when we relate this as theta of RS, as it is the dominating term. We don't say n squared, we don't say anything else of the sort. This is just telling us that as the rank and suit expand or don't, that's going to be what dictates how long this piece of code takes to run. Where possible, we want to use these kinds of elements. And we'll see this when we get into graph theory, because we will be looking at running times in terms of the number of vertices in those graphs, the number of edges on those graphs, but how many edges are there with respect to the number of vertices, that's going to change depending on the graph. So rather than trying to just make this n, we're going to see this in terms of the variables that are actually embedded in the underlying code, where possible. Any questions on that? Any questions on how we got here or how we got here from there? Pretty hate it. But yes.
I'm still a little bit confused because you said that R scales and S scales, right? Both of those are scaled with N, right? The size of our deck. So wouldn't we be able to look at R as, like what I was saying before, like N over whatever, and S over whatever, and then we get N?
Okay. So you would say it would be linear in terms of the size of the deck, and that's made up of 2 components, the ranks times the suits to get to the eventual deck size. I would count that as fine as well. Since you're allocating the memory in advance, hard coding this to be 52, terrible decision, by the way, never do that. This should be rank times suit, or something in terms of the variables that would scale in your code. Please do not put hard constants like that in your code. It's terrible design. The book that I pulled this from should know better, which is especially funny considering this was my professor.
What?
Those of you who took data structures, you had a textbook written by Peter Gray?
Oh yeah, very familiar, yeah.
Yeah, he was my professor.
Oh,
He taught me data structures and algorithms.
okay.
That's not why we used that book. We used it well before I got here, but it was very funny to see the book that he was writing while I was a student in his classes is now a book that we use in our classes.
Oh, that was surprising.
Small world.
Yeah, what a small world.
Other questions that I can answer before we move on? Because this room is so large and I tend to get tunnel vision, if you're on the edges, please do let me know if you have a question and I am not calling on you or recognizing that you exist. So thank you. All right. One more time. Let's play Go Fish.
No fish, no. Shuffle the deck and deal, you know, I do not need to see the hard costs. Let's see. Um. So, operations. Wowzers. How about that?
The bolded lines here, deck equals new deck and deck dot shuffle. Take your best guess at say how many operations those would require. Because that is not embedded in this code. What would it take in order to implement this? How many operations would that take?
Well, to get a new deck, it'd probably take one operation because you're just creating a new deck once. Shuffling it, however,
You're making a new deck once, but how many operations are responsible for making a new deck? When we before made that deck
oh,
as a constant size array, that's just allocating memory once. But when
oh,
we call a constructor for something, we probably have to do something in a loop, making a certain number of card objects.
oh, yeah, right, we did just go over that, didn't we?
It's assuming there's 52 cards in it.
Yeah,
Um. Shuffling the deck. Well, the new deck, we, yeah, what did the stuff we did? Just remind me of that quadratic. So now I'm just.
Assuming that.
Well, why did you write that?
it's a constant in your code. That should be a class constant. It's the hand size. If you hard code it at 7 and then somehow want to scale your game later and decide that, you know, maybe we should draw 10 cards initially, you have to go find everywhere you hard coded 7 in your code. If you miss one, you have a bug that you have to go find. Whereas if you pull that out of into a class constant, you change 1 7 into a 10 and you're done. It propagates throughout your code and you haven't made your own life miserable. So again, I'm yelling at my past professor to do better.
You have a very good point.
Maybe you thought Go Fish was perfect as it was.
Yeah, no one would ever need to do that. No one would ever need to change that starting hand.
Still. Still, yeah, you have good points. So, you know, they just go through that. When you're trying to do pictures for cars and no, think of something else.
But we are actually out of time for the day.
Oh, come on.
So I will leave this to you as a challenge. Work on this between today and tomorrow, and we will go over it first thing tomorrow morning.
Oh, before you get rid of it.
Yeah, absolutely. We can take a picture.
I was almost writing everything down. Almost.
Was getting me, you know, it's like.
I would assume that everything that is here is complete. It's just a matter of what's embedded in those functions.
Yeah, that's. Because I imagine. Okay. I'll do that, you know, right there, whatever, then it's gospel. And like, not being, I assume it's the same. Like, ideas of the water.
Yep.
Okay, there we go.
Question, how could you do that intelligently?
Yeah.